Hello there and welcome to the Twilight Archive, where we pause in the quiet hours to explore the moments that shaped everything we know. I'm your host, and tonight we're going to journey back through deep time to visit a chapter of Earth's story that most people have never heard of, but one that nearly ended all stories forever. We're going to the Permian-Triassic boundary, 252 million years ago, to witness what scientists call the Great Dying. The closest our planet has ever come to becoming a lifeless rock drifting through space. Now, you might be thinking about the asteroid that killed the dinosaurs. That's understandable. It's the extinction event that captures most of our attention, the one that gets the documentaries and the museum exhibits. But that cosmic impact, as devastating as it was actually just a minor tremor compared to what we're discussing tonight. The Great Dying wasn't quick like an asteroid strike. It wasn't clean. It was a slow-motion apocalypse that unfolded over hundreds of thousands of years, and when it was over, life on Earth had been reduced to barely more than microbial mats and a handful of struggling survivors. We're talking about numbers that are almost impossible to wrap your mind around. 96% of all marine species, gone. 70% of terrestrial vertebrates, vanished. Even insects, those masters of survival who seem to outlast everything, suffered their only known mass extinction. For a moment in geological time, Earth teetered on the edge of becoming another Mars, a dead world where the only movement would be dust blown by sterile winds. But here's what makes this story fascinating rather than simply terrifying. We're here to tell it. Life didn't end. Something survived, something persisted, and from that tiny remnant came everything that followed: the dinosaurs, the mammals, the forests, the coral reefs, and eventually us. The Great Dying is ultimately a story about the most profound resilience imaginable, written in the language of stone and time. How do we know about events from 250 million years ago? That's one of the beautiful things about geology. The Earth keeps meticulous records if you know how to read them. Every layer of rock is a page in a book, every fossil a word in a sentence that tells the story of ancient life. And what those rocks tell us about the end of the Permian period is both precise and unsettling. They show us the moment when the signature of abundant life simply stops. Picture yourself as a paleontologist working in the field, perhaps in the remote mountains of China or the desert formations of South Africa. You're examining rock layers that were laid down at the bottom of ancient seas, and you're finding fossils, brachiopods, trilobites, ancient corals, all the creatures that made the Permian oceans buzz with life. Then you reach a particular layer, a boundary marked by a thin band of rock that looks different from everything above and below it. And suddenly, the fossils disappear. Not gradually, not over millions of years as species slowly died out and were replaced by others, but quickly, geologically speaking. In the space of a few feet of rock, representing perhaps a few 100,000 years, an entire world vanishes. This boundary exists all over the planet. You can see it in China, in Russia, in Greenland, in Antarctica. Wherever you go, the story is the same: abundant life below, empty rock above. It's like walking through a library where all the books suddenly stop in the middle of the same sentence, on every shelf, in every room. What could cause such devastation? For decades, scientists puzzled over this question. Unlike the dinosaur extinction, there was no obvious smoking gun, no massive crater to point to as evidence of an asteroid impact. Instead, the evidence pointed toward something both more subtle and more devastating: a cascade of environmental changes so severe and so interconnected that once they began, they fed on themselves, growing worse and worse until the planet's life support systems simply collapsed. The prime suspect emerged from an unlikely place: Siberia. Not the Siberia of today, with its forests and tundra, but the Siberia of 252 million years ago, which was the site of volcanic activity so intense it defies easy description. We're not talking about a single volcano or even a chain of volcanoes. We're talking about an area roughly the size of Western Europe where the Earth's crust split open and began bleeding magma for nearly 1 million years. These were the Siberian traps, massive flood basalts that pumped not just lava but enormous quantities of toxic gases into the atmosphere. Carbon dioxide, sulfur compounds, chlorine, fluorine, and other chemicals that transformed the planet's chemistry in ways that life simply couldn't adapt to quickly enough. The atmosphere became a toxic soup, the oceans turned acidic, and temperatures soared beyond what most creatures could tolerate. But we're getting ahead of ourselves. To truly understand what happened during the Great Dying, we need to start at the beginning, in a world that was nothing like the wasteland it would become. We need to go back to the late Permian, to see life at its most abundant and diverse, to understand what we almost lost forever. You see, the Permian period wasn't just another chapter in Earth's history, it was the culmination of hundreds of millions of years of evolution. Life had finally figured out how to thrive on land. The first great forests had spread across the continents. Coral reefs built structures so massive they would dwarf anything we see today. Early reptiles were experimenting with new body plans that would eventually lead to dinosaurs and mammals. The diversity of life was staggering. And then, over the course of a few 100,000 years, a blink of an eye in geological terms, it was almost all destroyed. What survived was left to inherit an empty planet, a world so changed that it would take 10 million years to recover even a fraction of its former diversity. This is the story we're going to trace tonight, from the height of Permian abundance through the mechanics of destruction to the slow, difficult process of recovery. It's a story written in volcanic ash and fossil shells, in the chemistry of ancient oceans and the isotope signatures of long-dead organisms. And it's a story that has profound implications for understanding our own world and our own future. So let's begin our journey back through deep time, to the world before the catastrophe, when Earth was more alive than it had ever been, and had no idea what was coming. To understand what was lost in the Great Dying, we need to travel back 252 million years and see what Earth looked like when life was at its absolute peak. And I want you to forget everything you think you know about ancient worlds. This wasn't some barren, primitive landscape waiting for better things to come. This was Earth in full bloom. The late Permian period, that's what geologists call this time, was when our planet achieved something it had never managed before and hasn't managed since. It was the culmination of nearly 4 billion years of evolutionary experimentation, a world where life had figured out how to fill every possible niche, every available space, with a creativity and abundance that would make today's Amazon rainforest look sparse by comparison. Let's start with the oceans, because that's where the real spectacle was happening. Imagine diving into a Permian sea and finding yourself surrounded by coral reefs that stretched for thousands of miles. But these weren't the delicate branching corals we know today. These were massive, fortress-like structures built by creatures called rugose corals and tabulate corals, names that don't capture their majesty. Some of these colonial animals grew into domes the size of small buildings, creating underwater cities that hosted an almost incomprehensible diversity of life. Swimming through these reefs, you'd encounter creatures that looked like they were designed by someone with a very active imagination. There were brachiopods, animals that looked like ornate shells but were actually more closely related to worms than clams. They came in hundreds of varieties, each with its own intricate pattern of ridges and spines. Crinoids, often called sea lilies, carpeted the seafloor like underwater forests, their feathery arms filtering food from the water in synchronized waves. And then there were the ammonites. Picture a nautilus, but instead of the relatively simple shell we see today, imagine one with elaborate sutures and chambers, coiled in spirals or stretched into straight cones, some as small as coins, others with shells 6 feet across. These weren't primitive mollusks fumbling their way through ancient seas, these were sophisticated predators with eyes, tentacles, and jet propulsion systems that had been perfected over millions of years. But perhaps the most alien residents of these Permian seas were the brachiopods' distant cousins, the bryozoans. These were colonial animals that built lace-like structures, delicate as doilies but tough enough to survive in the strongest currents. They covered everything: rocks, shells, other animals, in intricate patterns that looked like fossilized snowflakes. Now, you might be thinking this sounds impressive, but surely the land was still relatively barren in those days? Here's where the late Permian gets really interesting. Life on land had been evolving for about 200 million years by this point, and it had figured out how to do things that wouldn't be seen again for tens of millions of years. The forests were unlike anything in our modern world. Instead of flowering plants, which hadn't evolved yet, you'd find vast swamps dominated by seed ferns, plants that looked like ferns but reproduced like pine trees. Some of these grew to enormous sizes, creating canopies 100 feet above the forest floor. Mixed among them were early conifers, tree ferns that rivaled redwoods in height, and something called Glossopteris, a seed fern with tongue-shaped leaves that dominated the southern continents. But it's the animals that really tell the story of Permian abundance. This was the age of the synapsids, the group that would eventually give rise to mammals, but at this point looked nothing like anything alive today. Picture a 6-foot-long predator called Inostrancevia, with massive saber teeth and a skull built like a bear trap. Or Scutosaurus, a plant eater the size of a rhinoceros, covered in armor plating and knobs that made it look like a walking fortress. These weren't clumsy, cold-blooded reptiles struggling to make their way in the world. Many of them were developing sophisticated temperature regulation, complex social behaviors, and hunting strategies that wouldn't be out of place in a nature documentary about African predators. Some, like the dog-sized Davinia, had differentiated teeth for cutting and grinding, a sign of the dietary specialization that would later characterize mammals. And here's something that might surprise you: many of these creatures were probably warm-blooded, or at least much closer to it than any reptile alive today. They had to be. The late Permian world was competitive in ways that demanded speed, endurance, and metabolic efficiency. This wasn't a world of sluggish giants waiting for the next evolutionary breakthrough. This was a world running at full throttle. The diversity numbers are staggering. Scientists estimate that there were more species alive during the late Permian than at any other time in Earth's history. The oceans teemed with thousands of different types of marine invertebrates. The land supported complex food webs with dozens of predator species, hundreds of plant-eating animals, and thousands of different plants. Even the insects had reached levels of diversity that wouldn't be seen again for millions of years. But perhaps most remarkably, these weren't separate ecosystems existing in isolation. The late Permian world was connected in ways that are hard to imagine today. Ocean currents carried nutrients and organisms across vast distances. Continental positions created climate patterns that supported rainforests from pole to pole. Rivers and shallow seas linked terrestrial and marine ecosystems in complex webs of interdependence. This was life's masterpiece, the result of nearly 4 billion years of trial and error, cooperation and competition, extinction and innovation. It was a world that had solved problems we're still working on today: how to support enormous biodiversity, how to create stable ecosystems, how to make every available resource count. And none of it knew what was coming. In the rocks of Siberia, forces were already stirring that would bring this magnificent world to an end. The creatures swimming through those vast coral reefs, the predators stalking through those ancient forests, the plants reaching toward a sun that had shone on life's greatest experiment, they were living in the final moments of Earth's golden age, and they had no idea that their time was almost up. So how do we know all this? How can we reconstruct such a detailed picture of a world that vanished 250 million years ago? The answer lies in what paleontologists call the rock record, layers of stone that preserve Earth's history like pages in an ancient book. But this isn't the kind of reading you learned in school. This is detective work on a geological scale, where every fragment tells part of a story that spans millions of years. Imagine you're standing in the Karoo Basin of South Africa, one of the most important fossil sites on Earth. The rocks here stretch back through the Permian period like a timeline written in stone. You can literally walk through millions of years, stepping from layer to layer, each one representing a slice of ancient time. And if you know what to look for, you can see the exact moment when the world changed forever. Paleontologist Roger Smith has spent decades reading these South African rocks, and he can show you something remarkable. In the lower layers, fossils are everywhere. Therapsids, those early mammal-like reptiles we met in the last section, are abundant. Their bones tell stories of diverse ecosystems, of predators and prey, of creatures adapting and thriving. The rock is alive with the signatures of ancient life. But then something happens. As you move up through the layers, representing movement forward through time, the fossils start to thin out. It's subtle at first, maybe fewer species, maybe smaller populations. But then you hit a boundary layer, a thin band of rock that represents the end Permian period. And above that line? The fossil record becomes nearly empty. Smith describes it as one of the most dramatic transitions he's ever seen in stone. Below the boundary, you might find dozens of different species in a single rock formation. Above it, you're lucky to find one or two. It's not gradual decline, it's collapse, preserved in perfect geological detail. Now, you might be wondering how we can be so precise about timing when we're talking about events from 252 million years ago. The answer lies in radiometric dating, one of geology's most powerful tools. Certain rocks contain radioactive elements that decay at known rates, like cosmic clocks ticking away at a perfectly steady pace. When we find volcanic ash layers mixed in with these fossil-bearing rocks, we can measure how much radioactive decay has occurred and calculate exactly when those ash falls happened. The precision is stunning. We can narrow down the timing of the Great Dying to within a few 100,000 years, which, on geological timescales, is like pinpointing a specific day in a human lifetime. And what we find is that this extinction didn't unfold over tens of millions of years, as some earlier extinctions did. It happened fast, geologically speaking, probably within about 200,000 years. But let's talk about what reading the rocks actually means in practice. Dr. Cindy Louie, a paleobotanist at the University of California, Berkeley, studies ancient plant life preserved in stone. She's found something particularly telling in rocks from this period, what she calls a disaster taxa. These are species that appear suddenly in the fossil record right after the extinction boundary, plants that seem perfectly adapted to disturbed, degraded environments. Think of them as the geological equivalent of weeds sprouting in a vacant lot after a building is demolished. Louie has found that these disaster plants dominated landscapes for millions of years after the extinction, suggesting that normal, complex ecosystems simply couldn't re-establish themselves. The rocks show us not just death, but the long, slow struggle of life trying to rebuild. Perhaps the most haunting evidence comes from what paleontologists call ghost ranges, the absence of fossils where we would expect to find them. In healthy ecosystems, certain types of creatures should appear consistently in the rock record. When they vanish suddenly and completely, their absence speaks as loudly as any fossil ever could. Take the rugose corals, for instance. These creatures built the reef systems that dominated Permian seas, creating some of the most biodiverse marine environments Earth has ever seen. Below the extinction boundary, their fossils are common, diverse, beautiful in their intricate patterns. Above that line? They're gone. Completely. The rugose corals never recovered from the Great Dying, their entire lineage ended forever. This is where the rock record becomes almost literary in its tragedy. We can trace these coral lineages through millions of years of evolution, see them diversify and spread across ancient oceans, watch them build magnificent reef cities beneath Permian seas. And then we find the layer where their story simply stops. Geochemist Paul Wignall from the University of Leeds has taken this detective work even further, analyzing the chemical signatures preserved in rocks from the extinction boundary. What is found adds another dimension to our understanding. The rocks don't just show us which creatures died, they show us how the environment itself changed. Wignall and his colleagues have discovered that the ocean chemistry at the time of the extinction was radically different from anything we see today. Sulfur isotopes in the rocks suggest that hydrogen sulfide, a toxic gas that smells like rotten eggs, was bubbling up from the deep ocean. Carbon isotopes tell us that massive amounts of carbon dioxide were flooding into the atmosphere. These aren't just fossils we're reading anymore, they're chemical fingerprints of a planet in crisis. What makes this rock record so compelling is its global consistency. You can find the same extinction signature in China, in Russia, in Greenland, in Antarctica. Wherever paleontologists look for rocks of the right age, they find the same story: abundant life below, almost nothing above. It's as if the entire planet pressed pause on evolution for millions of years. But here's what fascinates me most about reading these ancient rocks. We're not just looking at death, we're looking at the moment when Earth's future hung in the balance. Every fossil we find above that extinction boundary represents a lineage that somehow made it through the worst catastrophe in our planet's history. They're the ancestors of everything that came after, including, eventually, us. The rocks have given us the when, the where, and the who of the great dying. But they're also starting to reveal the how, the actual mechanisms that brought a thriving planet to its knees. And that story leads us deep beneath the surface of Siberia, to volcanic fires that burned for nearly 1 million years. But before we journey to those ancient volcanic hellscapes, we need to pause and truly grasp what we're talking about here. Because the numbers that define the great dying are so extreme, so far beyond anything in human experience, that they can start to feel abstract. 96% of marine species extinct. 70% of terrestrial vertebrates gone. These aren't just statistics, they're measurements of the closest our planet has ever come to becoming completely lifeless. Let's start with that marine figure, because it's the one that really stops scientists in their tracks. When we say 96% of marine species went extinct, we're talking about an ocean that was, for a brief moment in geological time, almost entirely empty. Imagine walking along a beach today and finding maybe one shell for every 25 you'd normally expect. That's the scale we're dealing with. But how do we even calculate something like this? You might be wondering how scientists can make such precise claims about events from 250 million years ago. It's a fair question, and the answer reveals something fascinating about how paleontology actually works. The process starts with what scientists call sampling, and it's more systematic than you might expect. Paleontologists don't just count every fossil they find and call it a day. Instead, they focus on specific time windows, usually measured in hundreds of thousands or millions of years. They'll examine rock layers from just before the extinction boundary, during the crisis itself, and in the recovery period afterward. Then comes the careful work of identification and comparison. Every fossil species gets catalogued, cross-referenced, and tracked through time. It's detective work on a geological scale. If a particular type of brachiopod, those shell creatures we met earlier, shows up in rocks from 253 million years ago but vanishes completely from rocks dated to 251 million years ago, and never reappears, that's marked as an extinction. Of course, there's always the possibility that we just haven't found the right rocks yet, or that some species survived in places where fossils don't preserve well. This is what paleontologists call the Lazarus effect, species that seem to go extinct but then reappear in the fossil record millions of years later. It happens, but it's rare enough that scientists can account for it statistically. What makes the great dying numbers so reliable is their consistency across different environments and different parts of the world. Whether you're looking at shallow tropical seas or deeper, colder waters, whether you're examining rocks from what is now China or South Africa or the American Southwest, the pattern holds. Life didn't just struggle in one region or one habitat, it collapsed everywhere, almost simultaneously. Now, let's think about what 96% extinction actually means in practical terms. In today's oceans, we have something like 230,000 known marine species. If the Great Dying happened tomorrow with the same intensity, only about 9,000 species would survive. That's fewer marine species than we currently have bird species on land. The terrestrial numbers are somewhat better, but only in the way that terrible is better than catastrophic. 70% of land vertebrates sounds almost manageable compared to the marine losses, until you really think about it. Picture the African savanna, the Amazon rainforest, the forests of North America, and then imagine 7 out of every 10 animal species simply gone. No more lions, no more elephants, no more wolves. The survivors would inherit a world that had become profoundly, eerily quiet. But there's something else hidden in these numbers that's even more unsettling. The Great Dying didn't just eliminate individual species, it dismantled entire ecosystems. When you lose 96% of marine life, you're not just losing a collection of creatures. You're losing the complex web of relationships that held those ecosystems together. Predator-prey relationships, symbiotic partnerships, the intricate food webs that had taken hundreds of millions of years to evolve, all of it unraveled in what paleontologists estimate was somewhere between 60,000 and 200,000 years. That might sound like a long time, but in geological terms, it's a blink of an eye. To put it in perspective, our own species has only existed for about 300,000 years. The Great Dying happened faster than humans have been around. Perhaps most remarkably, these extinction rates weren't uniform across all forms of life. Some groups were hit harder than others, and understanding these patterns gives us crucial clues about what was actually killing everything. Marine organisms suffered far more than terrestrial ones, which tells us something important about the nature of the crisis. Complex, multicelled organisms were hit harder than simple bacteria and archaea, suggesting that whatever was happening, it was particularly devastating to more sophisticated forms of life. There's also a size bias that shows up in the data. Larger organisms tended to die off more readily than smaller ones. This makes sense from an ecological perspective. Big animals need more resources, more stable environments, and more complex food webs to survive. When those systems collapse, the giants fall first. But perhaps the most haunting aspect of these numbers is how they compare to other mass extinctions. The event that killed the dinosaurs 66 million years ago eliminated about 75% of all species. The Great Dying was worse. Much worse. It's the only extinction event where scientists use words like near-total biological collapse. Yet somehow, impossibly, life persisted. That remaining 4% of marine species, that 30% of terrestrial vertebrates, they became the foundation for everything that came after. Every creature alive today, including us, traces its ancestry back through that tiny population of survivors who somehow endured the worst catastrophe in the history of complex life. These numbers force us to confront something profound about the nature of existence itself. Life on Earth has always been more fragile than we like to imagine, more dependent on stable conditions and complex interactions than our everyday experience suggests. The Great Dying shows us that even a planet teeming with life can be pushed to the very edge of silence. And that brings us back to those volcanic fires beneath Siberia, because understanding how such devastation was possible means understanding the forces that were reshaping the entire planet. So we find ourselves in Siberia, standing on ground that holds one of Earth's most devastating secrets. Today, this is a land of forests and tundra, cold winds, and endless horizons. But if you could travel back 252 million years, you'd witness something almost beyond imagination. This wasn't just an eruption, it was the largest volcanic event in our planet's recorded history. We call it the Siberian Traps, and the name tells us something important. Traps comes from the Swedish word trappa, meaning steps, because that's what these ancient lava flows look like today, giant staircases of dark rock stretching across an area larger than Europe. Think about that for a moment. Lava flows covering a region the size of Europe, stacked hundreds of meters thick in places. This wasn't Mount Vesuvius or even Mount St. Helens. This was volcanism on a continental scale. But here's what makes the Siberian Traps truly extraordinary: the duration. Most volcanic eruptions last days, weeks, maybe months. The Siberian Traps erupted for somewhere between 600,000 and 1 million years. Nearly 1 million years of continuous volcanic activity. Imagine trying to wrap your mind around that timeline. If these eruptions had started when humans first began writing, they'd still be going today. You might be wondering how we know all this. How do you study an eruption that ended 250 million years ago? Well, we start with what's left behind, those step-like formations of cooled lava, each layer a snapshot of ancient violence. Scientists can date these layers using radiometric techniques, measuring the decay of uranium and other radioactive elements trapped in the rock. When they do this across the entire region, a picture emerges of eruption after eruption, century after century, millennium after millennium. But the Siberian Traps weren't just pouring out lava. They were fundamentally changing the chemistry of Earth's atmosphere. Every time magma reached the surface, it released enormous quantities of gases: carbon dioxide, sulfur dioxide, hydrogen chloride, and other compounds that would prove toxic to life. We're talking about volcanic emissions on a scale that dwarfs anything in human experience. To put this in perspective, consider that the 1815 eruption of Mount Tambora, which caused global climate disruption, and the famous Year Without a Summer, released about 60 million tons of sulfur dioxide. The Siberian Traps, over their lifetime, may have released 100,000 times that amount. The numbers become almost meaningless at that scale, but the effects were anything but abstract. What makes this even more devastating is where these eruptions occurred. The Siberian Traps didn't erupt in the middle of an ocean where gases could be diluted and dispersed. They erupted on a continent, pumping their poisonous cocktail directly into the atmosphere where it could spread around the globe. And remember, this was the late Permian. The supercontinent Pangaea was still forming, which meant atmospheric circulation patterns were different from today, possibly making the global spread of volcanic gases even more efficient. Recent research has revealed another sinister aspect of these eruptions. As the magma rose toward the surface, it encountered thick layers of coal, salt deposits, and organic-rich sediments, exactly the kinds of materials you don't want to cook at volcanic temperatures. When magma meets coal, it doesn't just melt it. It converts it into additional carbon dioxide and toxic gases. When it hits salt deposits, it creates hydrogen chloride, essentially hydrochloric acid vapor. The Siberian Traps weren't just volcanic eruptions, they were inadvertently cooking the existing geology and turning it into an atmospheric poison factory. Scientists have found something particularly telling in the rock record. As you examine layers of sediment from this time period around the world, you find distinctive chemical signatures, isotope ratios that point directly back to Siberian volcanism. It's like finding fingerprints at a crime scene, except the crime scene is the entire planet and the fingerprints are molecular. The timing is perhaps the most damning evidence of all. The Siberian Traps began erupting right at the boundary between the Permian and Triassic periods, exactly when the Great Dying was reaching its peak. This isn't coincidence. This is cause and effect written in stone and measured in isotopes. But here's something that might surprise you. The immediate effects of the eruptions, The ash clouds, the local devastation, probably weren't what killed most of the planet's life. The real killer was more insidious, more gradual, and ultimately more complete. It was the slow, steady change in atmospheric chemistry that these eruptions caused over hundreds of thousands of years. Think of it this way. If you were standing next to an active Siberian trap volcano 252 million years ago, yes, you'd be in immediate danger from lava and toxic gases. But if you were a marine creature living in a coral reef thousands of miles away, your death sentence was being written by the same eruptions, just more slowly. The carbon dioxide and other gases released in Siberia would eventually make their way into the oceans, changing their chemistry in ways that would prove fatal. We can actually track this process in the geological record. As the eruptions continued, we see evidence of rising global temperatures, ocean acidification, and the spread of oxygen-dead zones in marine environments. Each of these changes can be traced back to the Siberian traps through chemical analysis of ancient rocks and fossils. What's truly sobering is realizing that this was all essentially unstoppable once it began. Unlike a meteor impact, which delivers its devastation in moments, the Siberian traps created a feedback loop of environmental destruction that fed on itself for nearly 1 million years. The initial eruptions changed the atmosphere, which changed the climate, which may have triggered even more volcanic activity, which changed the atmosphere further. And so we see how a geological event in one corner of Pangaea could trigger the greatest mass extinction in Earth's history. The Siberian traps show us that our planet's systems are more interconnected than we might imagine, and more vulnerable to disruption than we might hope. They transformed not just Siberia, but the entire world, setting in motion a cascade of environmental changes that would push life itself to the very brink of extinction. Now, you might think you understand what happens when the planet gets hot. After all, we live through summer heat waves. We've heard about global warming, we know that temperatures can rise. But what happened during the Great Dying wasn't just Earth getting warmer. It was Earth becoming something else entirely, a furnace world where the very chemistry of life broke down. Let's start with the numbers, because they help us grasp the scale of what we're talking about. Today, our planet's average temperature sits around 15 degrees Celsius, or 59 degrees Fahrenheit. During the late Permian, before the catastrophe began, Earth was already warmer than today, perhaps 16 to 18 degrees Celsius on average. But as the Siberian traps continued their relentless eruption, pumping carbon dioxide into the atmosphere year after year, decade after decade, century after century, something unprecedented began to happen. The greenhouse effect, which we often think of as a gentle warming process, became a runaway freight train. Carbon dioxide levels didn't just rise, they exploded. Some estimates suggest atmospheric CO2 concentrations reached levels 8 times higher than what we see today. 8 times. Imagine taking our current atmosphere and adding 7 more layers of greenhouse gases on top of it. But here's where the story gets truly terrifying, and where we begin to understand why this wasn't just a hot spell that life could wait out. As temperatures climbed, and we're talking about a rise of 8 to 10 degrees Celsius globally, with some regions seeing increases of 15 degrees or more, the planet's entire climate system began to unravel. Think about what happens to your body when you have a high fever. At 104 degrees Fahrenheit, you're in serious danger because your cellular processes start to break down. Your proteins begin to unfold, your enzymes stop working properly, your brain can't function normally. Now imagine that happening to an entire planet's worth of ecosystems, but slowly, over thousands of years, giving you just enough time to understand what's coming but not enough time to adapt. The first casualties were the forests. Trees, especially the massive coniferous forests that covered much of the late Permian landscape, simply couldn't survive the combination of heat and drought that the changing climate brought. We find evidence of this in the rock record layers where pollen virtually disappears, replaced by fungal spores. Fungi, you see, thrive on dead organic matter. These spore layers tell us about vast forests dying en masse, their corpses feeding an explosion of decomposer organisms. But the forest die-offs created their own feedback loop, and this is where we see the cascade effect that made the Great Dying so devastating. Dead forests can't absorb carbon dioxide. In fact, as they decomposed, they released even more CO2 into the atmosphere. The planet lost one of its most important natural carbon sinks just when it needed them most. And then there were the permafrost regions. Yes, even 252 million years ago, Earth had frozen soils in its polar regions. Locked away in ice were enormous quantities of organic carbon, perhaps even methane hydrates, those unstable compounds that exist only under very specific temperature and pressure conditions. As global temperatures soared, these frozen carbon stores began to thaw and release their greenhouse gases into the atmosphere. Now we're looking at a truly vicious cycle. Volcanic CO2 causes warming, which kills forests and melts permafrost, which releases more CO2, which causes more warming, which kills more forests and melts more permafrost. It's what climate scientists today call a positive feedback loop, though there's nothing positive about it. Once it gets started, it feeds on itself, accelerating beyond any hope of natural correction. But temperature alone wasn't the only killer. The extreme greenhouse conditions created weather patterns unlike anything in Earth's previous history. The superheated atmosphere could hold enormous amounts of water vapor, creating a world of devastating storms and floods in some regions, while others became deserts where temperatures regularly exceeded 50 degrees Celsius, hot enough to kill most complex life outright. You have to understand, most of the animals living during the late Permian had evolved during relatively stable climatic conditions. They had physiological systems adapted to their environments, metabolic processes that worked within certain temperature ranges, reproductive cycles tied to seasonal patterns that had been reliable for millions of years. When Earth became a greenhouse inferno, these finely tuned biological systems simply couldn't cope. Take the therapsids, those advanced mammal-like reptiles we met in our Permian world. Many of them were already experimenting with more active lifestyles, higher metabolic rates, perhaps even early forms of temperature regulation. But there's only so much any creature can do when the ambient temperature approaches the upper limits of what complex proteins can withstand. And here's something that really drives home the severity of what happened: even the insects struggled. Insects are typically among the most resilient creatures on Earth. They have short generation times, allowing for rapid evolution. They're small, requiring fewer resources. They're incredibly diverse, occupying every conceivable ecological niche. Yet during the Great Dying, insect diversity collapsed along with everything else. When even the insects can't adapt fast enough, you know you're dealing with environmental change on a scale that exceeds life's ability to respond. The heat also created what scientists call thermal stratification in the atmosphere, layers of air at different temperatures that don't mix well. This disrupted normal weather patterns, ocean currents, and atmospheric circulation systems that life had depended on for millions of years. The very movements of air and water that distribute heat, moisture, and nutrients around the planet began to break down. We can see evidence of this atmospheric chaos in the sedimentary rocks of the time. Instead of the regular, cyclical patterns we'd expect from normal seasonal changes, we find chaotic layers suggesting wildly variable conditions, floods followed by droughts, massive dust storms, sudden temperature swings that would challenge even the most adaptable organisms. But perhaps most ominously, the Greenhouse Inferno was just getting started. As we'll see, the superheated atmosphere was setting the stage for even more catastrophic changes in Earth's oceans, where the vast majority of life still lived. The furnace world was about to become something even worse, a planet where the very chemistry of life itself would be turned upside down. Let's imagine you're standing at the edge of the ocean during the height of the Great Dying. But this isn't the ocean you know. There are no waves crashing with white foam, no seabirds wheeling overhead, no fish jumping in the distance. The water stretches endlessly, dark and still, with an oily sheen that catches the toxic light filtering through the poisoned atmosphere. This is what the death of the seas looks like. We've talked about the furnace world that Earth had become, but for most life forms, the ocean was home. Even today, the sea holds far more biodiversity than land. So when we say that 96% of marine species vanished during the Great Dying, we're talking about the collapse of Earth's primary life support system. The question is, how do you kill an ocean? The answer lies in chemistry, and it starts with something as simple as carbon dioxide dissolving into seawater. You might remember this from high school chemistry. When CO2 mixes with water, it forms carbonic acid. It's a weak acid, the same stuff that gives soda its bite. Under normal circumstances, the ocean handles this just fine. It's been absorbing CO2 for billions of years. But during the Great Dying, normal was off the table. Those Siberian volcanoes we discussed weren't just pumping heat into the atmosphere. They were releasing carbon dioxide on a scale that defies comprehension. Modern humans release about 40 billion tons of CO2 per year, and that's already pushing our climate to dangerous extremes. The Siberian traps released that much every few months, for nearly 1 million years. The ocean, Earth's great carbon sink, was drowning in acid. Dr. Jonathan Payne at Stanford has spent years studying what this acidification did to marine ecosystems. When you drop the pH of seawater even slightly, something remarkable and terrible happens to any creature that builds a shell or skeleton from calcium carbonate. The acid begins to dissolve these structures, literally eating them away. Imagine trying to live in a house that's slowly being dissolved by rain. That was the reality for countless marine species. Corals, which had built vast reef systems that rivaled anything we see today, simply melted away. Brachiopods, those abundant filter feeders that had dominated seafloors for hundreds of millions of years, couldn't maintain their shells. Trilobites, those iconic arthropods that had survived previous mass extinctions, finally met their match. The chemistry of life itself was under assault. But acidification was only the beginning. As surface temperatures soared, something even more sinister was happening in the deep ocean. Warm water holds less dissolved oxygen than cold water, that's basic physics. As the planet heated, the oceans began to suffocate. We call these regions hypoxic zones, areas where oxygen levels drop so low that complex life simply cannot survive. Today, we're seeing hypoxic zones expand in our own oceans, creating what scientists grimly call dead zones. The Gulf of Mexico has one the size of Massachusetts. But during the Great Dying, these dead zones weren't isolated patches. They were spreading like a slow-motion tsunami throughout the world's oceans, growing larger and more toxic with each passing century. Lee Kump at Penn State has modeled how this process would have unfolded. Picture the ocean as a layered system, with warm surface waters sitting on top of cooler, denser water below. Normally, currents mix these layers, bringing oxygen-rich surface water down to the depths. But extreme warming disrupts this circulation. The surface waters become so hot and light that they form a kind of lid, trapping the deeper waters below. Down in those isolated depths, bacteria went to work decomposing the rain of dead organisms falling from above. This process consumes oxygen and produces hydrogen sulfide, the same gas that gives rotten eggs their smell, but far more deadly. These purple and green sulfur bacteria had been around since Earth's early days, but they'd been largely relegated to the margins of life. Now they were inheriting the ocean. The fossil record tells us this story with unsettling clarity. In rock layers from the Great Dying, we find what paleontologists call biomarkers, molecular fossils that reveal which organisms were thriving. Normal marine ecosystems leave behind signatures of diverse life: algae, zooplankton, fish, everything you'd expect. But in the extinction layers, we find something else entirely. The molecular signatures of sulfur bacteria dominate, painting a picture of seas that had essentially become giant bacterial mats. You might be wondering how we can be so specific about ocean chemistry from 250 million years ago. The answer lies in isotopes, different versions of the same element that behave slightly differently in chemical reactions. When paleochemist Clitty Grice analyzed rocks from this period, she found isotope signatures that could only come from massive blooms of sulfur-producing bacteria. The ocean had become a toxic soup. This wasn't happening quickly, mind you. We're talking about changes that unfolded over hundreds of thousands of years. But from the perspective of evolution, this was lightning fast. Species that had taken millions of years to evolve were being wiped out faster than new ones could emerge. The ocean's food webs, built up over geological ages, collapsed like a house of cards. What makes the marine extinction so devastating is that the ocean should have been a refuge. On land, creatures could potentially migrate to cooler regions or higher elevations. But the ocean is one connected system. There was nowhere to run. The chemistry of the entire planetary ocean was changing, creating a global death trap. The few marine creatures that survived this oceanic apocalypse were remarkable in their simplicity. Small, hardy organisms that could tolerate low oxygen, high acidity, and toxic conditions. They were the marine equivalent of disaster species, the organisms that thrive in disturbed environments but struggle in complex ecosystems. As we move forward in our story, we'll discover that the dying oceans were about to become something even worse. Because those bacterial blooms weren't just consuming oxygen and producing hydrogen sulfide in the water. They were beginning to pump that toxic gas into the atmosphere itself, creating what some scientists believe was the final, killing blow. The ocean wasn't just dying, it was becoming a weapon against the remaining life on Earth. And so we arrive at something that feels almost like science fiction, but the evidence is written in the rocks themselves. Picture this: you step outside on what should be a normal morning, but the air carries a smell that makes your stomach turn. It's the unmistakable odor of rotten eggs, but magnified beyond anything you've ever experienced. This isn't coming from some distant swamp or sulfur spring. This is the atmosphere itself, poisoned with hydrogen sulfide gas. For life during the Great Dying, this nightmare scenario wasn't fiction. It was the final chapter of Earth's greatest catastrophe. Now, you might be wondering how we know this happened. How do scientists piece together the chemistry of air from 252 million years ago? The answer lies in a detective story that spans continents and requires some of the most sophisticated analytical tools we have. When researchers examine rock samples from the end Permian boundary, they find something unsettling: isotopic signatures that tell the story of a world drowning in its own toxic breath. Let me walk you through what we think happened. Remember those massive dead zones we discussed spreading across the oceans? Those weren't just empty patches of water. They were vast bacterial factories, and the bacteria thriving in those oxygen-starved depths were producing something far more sinister than carbon dioxide. In the absence of oxygen, certain types of bacteria switch to a different kind of metabolism. Instead of breathing oxygen like we do, they process sulfur compounds, and their waste product is hydrogen sulfide, one of the most toxic gases on Earth. Here's where the story gets truly frightening. As more and more of the ocean became depleted of oxygen, these bacterial communities exploded in size. We're talking about bacterial blooms that covered areas larger than entire modern countries. And all of that bacteria was pumping hydrogen sulfide into the water, and eventually, into the atmosphere above. To understand just how deadly this was, let's do a thought experiment. Imagine you're standing on the shore of one of these ancient seas. The water before you looks different, maybe darker, with an oily sheen that catches the light in unsettling ways. But it's the smell that hits you first, that rotten egg odor so intense it makes your eyes water. You take a breath, and immediately your body rebels. Hydrogen sulfide isn't just unpleasant at high concentrations, it's one of nature's most efficient killers. This gas attacks life at the cellular level, disrupting the very machinery that allows cells to produce energy. Even small amounts can cause respiratory failure. Higher concentrations can kill within minutes. For the creatures of the late Permian, there was nowhere to run. The poison was everywhere, in the water, in the air, seeping into every corner of their world. Now, we need to be careful here. The hydrogen sulfide hypothesis is still being debated in scientific circles. Some researchers, like Peter Ward from the University of Washington, have championed this idea based on geological evidence and computer models. Others point out that we're still learning about the complex chemistry of ancient atmospheres. But the evidence is compelling, and it fits with what we see in the fossil record. Let's examine that evidence more closely. When scientists study the carbon isotope ratios in rocks from this period, they find signatures consistent with massive bacterial production of hydrogen sulfide. They also find evidence of what's called photic zone euxinia, a fancy way of saying that even the sunlit surface waters of the ocean became toxic and oxygen-free. This is almost unprecedented in Earth's history, and it suggests that the normal cycles that keep our oceans healthy had completely broken down. The timing is crucial here. This wasn't a quick poison pulse, it was a slow strangulation that lasted thousands of years. As the Siberian volcanism continued pumping greenhouse gases into the atmosphere, and as the oceans warmed and became more acidic, the conditions became perfect for these hydrogen sulfide-producing bacteria to thrive. It was a positive feedback loop from hell. The worse conditions became, the more toxic gas was produced, which made conditions even worse. For life on land, this was perhaps the cruelest twist of all. Creatures that had managed to adapt to the extreme heat, that had found ways to cope with the acid rain and the changed chemistry of rivers and lakes, now faced an atmosphere that was literally poisonous to breathe. The gas would have been heaviest in coastal areas and low-lying regions, exactly where many ecosystems were already struggling to survive. You have to understand, this wasn't like modern air pollution, where we can retreat indoors or move to cleaner areas. This was planetary-scale atmospheric poisoning. The hydrogen sulfide would have mixed with the existing cocktail of volcanic gases, creating a toxic soup that blanketed much of the Earth's surface. Some researchers have suggested that the gas concentrations may have reached levels that would be lethal to humans within hours. The evidence suggests that this poisoning may have been the final straw for many ecosystems that were already hanging by a thread. Marine environments, already devastated by heating and acidification, were hit hardest. But even terrestrial ecosystems, which had shown more resilience up to this point, began to collapse as the toxic atmosphere took hold. It's important to note that not all scientists agree on the extent of hydrogen sulfide poisoning, or whether it was truly global in scale. Some argue that the gas would have been quickly broken down by ultraviolet radiation in the upper atmosphere, limiting its spread. Others suggest that local effects, while devastating, may not have been the primary driver of the extinction. The science is still evolving, and new analytical techniques are constantly refining our understanding of this ancient catastrophe. But here's what we do know: something pushed the Great Dying beyond the normal bounds of mass extinction. The combination of extreme heat, ocean acidification, and atmospheric toxicity created conditions that were simply incompatible with complex life as it had evolved. The numbers don't lie: 96% of marine species vanished, and the fossil record shows a complexity crash that lasted for millions of years. As we piece together this ancient catastrophe, we're left with a sobering realization. Earth became, for a time, genuinely hostile to the very life it had nurtured for billions of years. the air itself became an enemy. And yet, somehow, in the face of this planetary poisoning, life found a way to persist. The question we turn to next is perhaps the most remarkable of all: who survived when survival seemed impossible? Who made it through Earth's darkest hour? We meet the unlikely survivors, small, adaptable creatures that would inherit an empty world and eventually give rise to dinosaurs and mammals. Picture the Earth 252 million years ago, in the immediate aftermath of the Great Dying. The landscape stretches before us like something from another planet entirely, barren, scarred, almost alien in its emptiness. The great forests are gone, reduced to scattered stumps and ash. The coral reefs that once teemed with life lie bleached and broken. The air still carries traces of poison, and the soil bears the chemical signature of catastrophe. This is a world that has been, quite literally, reset. Yet if you look closely, very closely, you'll notice something extraordinary. Life persists. Not the abundant, diverse communities we've been exploring, but something far more humble. Something that managed to thread the needle between extinction and survival when the odds were impossibly stacked against them. Who were these survivors? The answer surprises many people. They weren't the biggest, strongest, or most dominant creatures of their time. They weren't the apex predators or the ecosystem engineers. Instead, the survivors shared a few crucial characteristics that we're only now beginning to fully understand. They were small. They were generalists. And perhaps most importantly, they were extraordinarily good at dealing with scarcity. Let's start with one of the most important survivors, a creature you've probably never heard of, but one whose descendants would eventually rule the world. Meet Lystrosaurus, a pig-sized reptile that, frankly, doesn't look like much. Imagine a creature with a barrel-shaped body, stumpy legs, and a turtle-like beak. Not exactly what you'd call impressive. But Lystrosaurus had something that the magnificent predators and towering herbivores lacked: flexibility. Before the Great Dying, Lystrosaurus was just one species among thousands. After the extinction, paleontologists find something remarkable in the fossil record. In some early Triassic rock formations, Lystrosaurus fossils make up 95% of all vertebrate remains. 95%. This humble creature had inherited the Earth. What made Lystrosaurus so successful? We think it comes down to diet and metabolism. While other herbivores specialized in particular types of plants, Lystrosaurus could eat almost anything green that grew from the ground. Tough roots, scraggly shrubs, whatever sparse vegetation managed to survive, Lystrosaurus made it work. Their beak-like mouths were perfect for this kind of opportunistic feeding, and their digestive systems could extract nutrients from even the poorest quality plant matter. But Lystrosaurus wasn't alone in the wasteland. Other survivors emerged from different corners of the tree of life, each with their own survival strategies. Small carnivorous reptiles called archosaurs, the group that would eventually give rise to crocodiles and dinosaurs, made it through by being adaptable predators. When large prey became scarce, they hunted smaller animals. When meat was hard to find, some may have scavenged or even eaten insects and other invertebrates. The mammal ancestors, tiny, shrew-like creatures called cynodonts, survived by literally going underground. Many of these early proto-mammals had already evolved burrowing behaviors, which proved invaluable when the surface world became uninhabitable. Underground, temperatures were more stable, oxygen levels were higher, and there was protection from the toxic atmosphere above. These burrows became nurseries for the future, sheltering the lineage that would eventually give rise to everything from mice to whales to us. What's fascinating is how the rules of survival shifted during this crisis. Before the Great Dying, success in the Permian often meant specialization. The most successful creatures were those perfectly adapted to specific environments: coral reef specialists, particular types of hunters, herbivores that could process specific plant toxins. but specialization became a death sentence when environments collapsed. The survivors were the generalists, the creatures that were, in evolutionary terms, good enough at many things rather than perfect at one thing. They could eat a variety of foods, tolerate a range of environmental conditions, and adjust their behavior when circumstances changed. In the devastated world of the early Triassic, being a jack of all trades was far more valuable than being a master of one. Size mattered too, but not in the way you might expect. Larger animals require more resources, more food, more oxygen, more space. In a world where all of these were suddenly scarce, small body size became an enormous advantage. Small animals could survive on less, reproduce more quickly, and find shelter in places larger creatures couldn't access. The meek, quite literally, inherited the earth. We see this pattern repeated in marine environments as well. The survivors in the oceans were small, simple creatures, tiny gastropods, some bivalves, and primitive arthropods. The complex reef ecosystems were gone, but simple organisms that could tolerate low oxygen, high acidity, and temperature fluctuations managed to persist in marginal environments. Interestingly, many of these survivors also shared another trait: they were relatively young as species. The creatures that had evolved most recently were often the ones best equipped to handle rapid environmental change. This makes sense when you think about it. Newer species had evolved under already changing conditions, while ancient lineages were more set in their evolutionary ways. There's something both humbling and hopeful about this story. The survivors of Earth's greatest crisis weren't the magnificent apex predators or the perfectly adapted specialists. They were the small, the flexible, the humble creatures that could make do with less. They were the evolutionary equivalent of that person in your friend group who can sleep on any couch, eat any food, and somehow find the bright side of any situation. But here's what makes this survival story truly remarkable: these weren't just holdouts clinging to existence. These survivors carried within their genes the potential for an entirely new chapter in Earth's history. The small archosaurs would eventually give rise to the largest land animals that ever lived, the dinosaurs. The tiny protomammals would diversify into the incredible array of mammalian life we see today. Even humble Lystrosaurus played a crucial role, maintaining herbivorous ecosystems until other plant eaters could evolve to replace it. The survivors of the Great Dying teach us that evolution doesn't always favor the biggest, strongest, or most dominant. Sometimes, it rewards the patient, the adaptable, and the resourceful. These creatures didn't just survive, they laid the foundation for life's greatest comeback story. But that recovery would be neither quick nor easy, as we're about to discover. Picture standing in a library after a devastating fire. Books reduced to ash, shelves collapsed, the very architecture of knowledge destroyed. Now imagine trying to rebuild that library from memory, with only a few scattered survivors who remember fragments of what was lost. This is the challenge life faced in the aftermath of the Great Dying. Recovery wasn't just about species bouncing back, it was about reconstructing the entire framework of how ecosystems function. When we talk about recovery in deep time, we're not discussing months or even centuries. We're looking at a process that unfolded over 10 million years. 10 million years. To put that in perspective, our entire human species has existed for only about 300,000 years. The recovery from the Permian extinction took longer than the dinosaurs ruled the Earth. Why did it take so long? The answer lies in understanding what extinction events really destroy. It's not just individual species, it's the relationships between them. Think of an ecosystem as a vast web of connections. Predators depend on prey, plants rely on pollinators, decomposers break down organic matter. The Great Dying didn't just remove species from this web, it shredded the web itself. And rebuilding those connections, those intricate relationships that make ecosystems work, takes time. Lots of time. Let's follow this recovery through the fossil record, and we'll discover it happened in stages, like a building being reconstructed floor by floor. The first phase, lasting about 2 to 3 million years after the extinction, was what paleontologists call the disaster interval. This isn't the extinction itself, this is the long, difficult period when life was trying to get back on its feet. During these early recovery years, we see something fascinating in the rocks. The fossil record shows us communities dominated by just a few types of organisms. Remember those hardy survivors we met earlier? Small brachiopods, simple mollusks, opportunistic creatures that could handle harsh conditions, they were the first to spread out into the empty world. But these weren't diverse, complex communities. They were more like pioneer species moving into abandoned territory. You might wonder why these survivors couldn't just diversify quickly to fill all the empty ecological niches. After all, with so much space available and so little competition, shouldn't evolution have raced to fill the gaps? The problem was environmental instability. Even though the worst of the extinction was over, Earth systems were still chaotic. Ocean chemistry was still recovering. The climate was still unstable. Volcanic activity was still ongoing in some regions. It's hard for life to diversify and specialize when the basic rules of survival keep changing. As we move through the rock record, something shifts around 4 to 5 million years after the extinction. Paleontologists call this the beginning of the true recovery phase. This is when we start to see the first signs of ecosystem complexity returning. New types of marine organisms appear. Reef building begins again, though these aren't the massive coral reefs of the Permian, they're smaller, simpler structures built by different types of organisms entirely. On land, the picture was equally gradual. Those small reptiles and amphibians that survived began to diversify, but slowly. Very slowly. Think about why this might be. In a world where most plant species had gone extinct, the survivors had to rebuild the foundation of terrestrial food webs from the ground up. Literally. Soils had to be rebuilt. Plant communities had to establish themselves. Only then could herbivores diversify, and only after that could predators follow. Here's something remarkable that the fossil record reveals: the organisms that eventually dominated the post-extinction world weren't necessarily the same types that had survived the initial catastrophe. Many of the disaster interval survivors were evolutionary dead ends. They were great at surviving crises, but not at evolving into new forms. The real winners of recovery were often groups that had barely made it through the extinction, small populations that had clung to existence and then exploded into new evolutionary possibilities once conditions stabilized. This is where we meet some familiar faces in Earth's story. Among the reptiles diversifying in this recovery period were the earliest archosaurs, the group that would eventually give rise to both dinosaurs and crocodiles. Small, unassuming creatures during the Permian extinction, they found their moment in the recovery. And in the oceans, new types of marine reptiles began to appear, setting the stage for the great marine predators of the Triassic. But even after 5 million years of recovery, ecosystems weren't back to their pre-extinction complexity. The final phase of recovery took another 5 million years, bringing us to about 10 million years total. This is when we finally see ecosystems that rival the complexity of what was lost. Diverse marine communities. Complex terrestrial food webs. The return of large predators and specialized ecological relationships. Why did this final phase take so long? We're looking at the most difficult part of ecosystem reconstruction, the evolution of complex, interdependent relationships. It's one thing for different species to coexist in the same environment. It's quite another for them to develop the intricate partnerships and dependencies that characterize mature ecosystems. Think of plant-pollinator relationships, complex predator-prey dynamics, or the elaborate symbiotic partnerships we see in healthy ecosystems today. These relationships require evolutionary fine-tuning that simply takes time. There's something both humbling and hopeful in this 10 million year timeline. Humbling because it reminds us that when we talk about environmental damage, recovery operates on timescales that dwarf human civilization. But hopeful because it demonstrates life's extraordinary persistence. Even after losing 96% of species, even after 10 million years of slow rebuilding, life not only recovered but eventually exceeded its previous complexity. As we trace this recovery through the rock record, we're watching more than just the return of biodiversity. We're witnessing the reconstruction of Earth's life support systems. The return of complex carbon and nitrogen cycles. The re-establishment of marine and terrestrial productivity. The rebuilding of the intricate chemical and biological processes that make our planet habitable. And here's something that connects this ancient recovery to our modern world. The species that emerged from this long rebuilding weren't just survivors of catastrophe, they were the ancestors of almost everything we see around us today. That 10 million year recovery didn't just restore life to Earth. It set the stage for the entire Mesozoic era, the age of dinosaurs, and ultimately, the evolutionary path that led to us. But before we explore what this ancient catastrophe might teach us about our modern challenges, we need to look more closely at the connections between past and present. So here we are, looking back across 252 million years at Earth's closest brush with becoming a dead world. You might be wondering what relevance this ancient catastrophe has for us today. After all, we're not dealing with continent-sized volcanic eruptions or million-year firestorms. But when we examine the Great Dying closely, the parallels to our modern environmental crisis become impossible to ignore, and they're both more troubling and more hopeful than you might expect. Let's start with the most obvious connection: carbon dioxide. The Siberian traps pumped massive amounts of CO2 into the atmosphere over hundreds of thousands of years, fundamentally altering Earth's climate system. We're doing something remarkably similar, just faster. Since the Industrial Revolution began, we've released more carbon dioxide into the atmosphere in 2 centuries than those ancient volcanoes did in millennia. The chemistry is identical: carbon atoms bonding with oxygen, trapping heat, acidifying oceans. The only difference is the source and the speed. This speed difference is crucial, and it cuts both ways. During the Great Dying, ecosystems had time to shift, to migrate, to adapt, but ultimately, even that extended timeline wasn't enough. The changes were too severe, too all-encompassing. Today's rapid changes give life less time to adjust, but they also offer us something the Permian world didn't have: the awareness and the possibility of intervention. Consider the ocean chemistry. Ancient seas became acidic as CO2 dissolved into seawater, creating conditions that dissolved the shells and skeletons of marine organisms. We're seeing the early stages of this same process today. Coral reefs, those vibrant underwater cities, are experiencing bleaching events that would have been unthinkable just decades ago. The pH of our oceans has dropped measurably since we began burning fossil fuels. We're conducting the same experiment that helped kill 96% of marine species, just in fast forward. But here's where the story becomes more complex. The Great Dying wasn't caused by a single factor, it was a cascade of interconnected failures. Rising temperatures led to ocean stagnation. Stagnant waters became oxygen-free dead zones. Dead zones produced hydrogen sulfide. Each crisis fed the next, creating a runaway disaster that the planet's systems couldn't correct. Scientists call this a positive feedback loop, though there's nothing positive about it. We can see similar feedback loops beginning to emerge in our modern world. Arctic ice reflects sunlight back to space, keeping our planet cool. As that ice melts due to warming, it exposes dark ocean water that absorbs more heat, leading to more melting. Permafrost contains vast stores of carbon that have been frozen for thousands of years. As temperatures rise and permafrost thaws, that carbon enters the atmosphere as methane and CO2, accelerating warming further. Yet there's a crucial difference between the Permian extinction and our current situation. The ancient world had no choice but to endure whatever the Siberian traps threw at it. Volcanic eruptions operate on geological timescales, beyond any possibility of control or mitigation. We, however, are the agents of change. What we've caused, we can potentially modify or stop. This is where the story of recovery becomes essential. Remember those 10 million years it took for life to fully bounce back after the Great Dying? That timeline isn't just a historical curiosity, it's a warning about the true costs of ecosystem collapse. When we lose species today, when we simplify food webs and destroy habitats, we're not just creating temporary problems. We're potentially setting back biological recovery by millions of years. But the survivors of the Great Dying also offer us hope. Life found a way through Earth's worst crisis by being adaptable, by being small, by being opportunistic. The creatures that made it through weren't necessarily the strongest or the most specialized, they were the most flexible. Today's conservation efforts often focus on preserving this same kind of resilience, maintaining genetic diversity, protecting habitat corridors that allow species to migrate, supporting ecosystem functions rather than just individual species. Perhaps most importantly, the Great Dying teaches us about the power of early intervention. By the time hydrogen sulfide was poisoning the atmosphere, it was far too late to prevent catastrophe. The critical moment for intervention was much earlier, when CO2 levels first began to spike, when temperatures started their inexorable rise. The lesson for us is clear: environmental problems that seem manageable in their early stages can rapidly become unstoppable. There's another parallel worth considering: the role of life itself in both causing and surviving these crises. The Great Dying was partly driven by biological processes, bacteria producing toxic gases in oxygen-starved seas, decomposing organic matter releasing more carbon. Life wasn't just a victim of the catastrophe, it was also an unwitting participant. Today, we're learning to harness biological processes to help solve our environmental challenges: forests that sequester carbon, wetlands that filter pollutants, microorganisms that break down plastics. The geological record shows us something remarkable about our planet. It has experienced climate changes far more extreme than anything we're currently facing, yet life persisted. Earth has been a snowball and a hothouse. It has endured asteroid impacts and supervolcanic eruptions. Through it all, life has not just survived but eventually thrived again. This isn't cause for complacency. Mass extinctions are still mass extinctions, with suffering and loss on an unimaginable scale. But it does suggest that life, including perhaps human life, has more resilience than we sometimes imagine. The Great Dying ultimately reminds us that we're part of a much larger story, one that stretches back hundreds of millions of years and will continue long after we're gone. But we're also a unique chapter in that story. We're the first species capable of understanding these deep patterns, of learning from ancient catastrophes, of potentially choosing a different path. We can read the rocks, decode the chemistry, and see the warning signs that our predecessors never could. As we move toward our final thoughts about this remarkable story of destruction and renewal, we carry with us both the sobering lessons of the past and the unprecedented opportunities of the present. The Great Dying shows us what's possible when environmental systems collapse, but it also shows us that even the worst disasters are not necessarily the end of the story. And so we arrive at the end of our journey through Earth's darkest chapter, but perhaps that's not quite right. Maybe we're not at the end at all, maybe we're standing at the beginning of something else entirely. Because when you really think about what we've discovered together over these past hours, the story isn't fundamentally about death. It's about something far more extraordinary. We began tonight by asking how life survived the unsurvivable, and along the way, we've witnessed something that defies every reasonable expectation. We've seen a planet transform into what any reasonable observer would call a hellscape, temperatures soaring beyond anything multicellular life had ever experienced, oceans turning to acid, the very air becoming poison. We've calculated the numbers and they're staggering: 96% of marine species erased, ecosystems that had flourished for millions of years reduced to nothing more than traces in the rock record. But here's what strikes me as we reach the end of this story. Every single one of us listening right now, you, me, every living thing on this planet, we're all descended from the survivors of that catastrophe. Think about that for a moment. The neurons firing in your brain as you process these words, the oxygen you're breathing, the very fact that complex life exists at all, it's all because a handful of small, seemingly unremarkable creatures managed to endure what should have been impossible to endure. The more we study the Great Dying, the more we realize that survival wasn't about being the strongest or the largest or even the most well-adapted to pre-catastrophe conditions. The survivors were often the smallest, the most generalized, the ones that could eat almost anything and live almost anywhere. They were, in many ways, unremarkable, until the moment they became the most remarkable creatures in Earth's history simply by continuing to exist. Consider the humble Lystrosaurus, that pig-sized herbivore we met earlier. Before the extinction, it was just one species among thousands, nothing particularly special about it. But when the dust settled and the poison cleared, Lystrosaurus found itself inheriting an empty world. For a brief moment in geological time, this single species made up 95% of all terrestrial vertebrate life on Earth. Every mammal that would ever exist, every dinosaur that would ever walk the Earth, every bird that would ever take flight, they all lived in the shadow of Lystrosaurus's unlikely triumph. And this points us toward something profound about the nature of life itself. We often think of survival as a zero-sum game, as if the universe is constantly testing life and finding it wanting. But the Great Dying suggests something different. It suggests that life has a quality that we might call, for lack of a better word, persistence. Not just the ability to survive, but something deeper, the tendency to keep trying, to keep experimenting, to keep pushing into every available niche and possibility. You see this in the fossil record's most remarkable feature, not what's missing, but what appears next. Within just a few 100,000 years of the Great Dying, a blink of an eye in geological terms, new species were already beginning to radiate outward, filling the empty spaces left behind. These weren't just copies of what came before. They were experiments, innovations, entirely new approaches to the problem of staying alive on a dangerous planet. The Great Dying gave us the Mesozoic era, the age of dinosaurs, simply because it cleared the stage for reptiles to explore possibilities that had never existed before. Without that catastrophe, mammals might never have evolved beyond small, nocturnal creatures living in the shadows. The extinction that nearly ended everything instead became the beginning of almost everything we recognize in the modern world. This tells us something important about catastrophes themselves. We tend to think of them as pure destruction, as forces that only subtract from the world's possibilities. But the Great Dying shows us that catastrophes can also be creative forces, terrible and destructive, yes, but also transformative in ways that gradual change never could be. Now, as we've discussed, this doesn't mean catastrophes are good things or that we should welcome them. The suffering embedded in the fossil record of the Great Dying is real and immense. Entire lineages that had existed for hundreds of millions of years vanished forever, and there's genuine loss in that. The early synapsids, the trilobites, the magnificent reefs of the Permian, they're gone, and no amount of subsequent evolution can bring them back. But here's what gives me hope as we consider our own relationship with planetary change: life doesn't just survive catastrophes, it learns from them. The survivors of the Great Dying weren't just lucky, they possessed traits that proved valuable in a transformed world. And in many cases, those traits were things like adaptability, cooperation, and the ability to thrive in disturbed environments. Today, as we face our own period of rapid environmental change, we're not starting from zero. We're the inheritors of 4 billion years of evolutionary problem-solving, including the hard-won lessons of the Great Dying. We carry in our cells and our genes and our behaviors the accumulated wisdom of every organism that ever survived a crisis. More than that, we're the first species in Earth's history that can actually study these ancient catastrophes, understand their causes, and potentially learn from them in real time. We can read the rocks, decode the chemistry, and see the patterns that our ancestors lived through blindly. That's not a small thing. That's unprecedented. As we close this journey through deep time, I want you to remember something. The same forces that created the Great Dying, volcanism, climate change, ocean chemistry, they're all still active on our planet. Earth hasn't become safe, it's still the same dynamic, sometimes violent world it's always been. But life has become something extraordinary, not just adapted to this world, but actively engaged in shaping it. We are, all of us, part of life's indomitable spirit. We're not separate from the story we've been telling tonight, we're the latest chapter in it. And if the fossil record teaches us anything, it's that the story is far from over. Thank you for joining me in the Twilight Archive, where even the darkest chapters of Earth's history reveal the extraordinary resilience of life itself.